Thank you, Ben. That's a lot more praise than I deserve, and I'm very grateful to be here. This is my second presentation. I was at the previous AISoLA, and I hope to keep coming back to every AISoLA, so as long as you'll have me. So as Bernhard mentioned, I was formerly at DARPA. As of 2 months ago, I transitioned to an academic career at the University of Colorado Boulder. And what I'd like to talk about today has to do with the portfolio that I was growing when I was at DARPA. So I had 3 large programs. They were all focused on neurosymbolic AI as it applies to various domains where generalization is very difficult. So these are the domains of autonomy, going from simulated autonomy to real-world platforms, or what we call the sim to real gap. Biology, going from natural biology to synthetic biology, or what I like to call the natural to synthetic gap. And scientific discovery, going from exploratory creativity to truly transformational ideas. If you ask the question, can an AI discover a Nobel-worthy result? Today, the answer seems to be no. But we think there are ways that we can actually get there. And so I want to talk about all these gaps. Everything I'm going to discuss today is highly speculative, half-baked, exploratory. So this is more a call to action or collaboration. If any of these ideas interest you, if you want to talk about collaborating, these are things that we're actively looking into. But before I get into those gaps, there is an even more fundamental gap that is hiding within the gaps. And this is the gap of scale. When you look at current AI, current models are so expensive to develop from scratch that in and of itself imposes a gap. So when you look, for example, this comes out of Stanford's AI report. When you look at the cost to train Google Gemini Ultra, which is one of their big foundation models, over 1 trillion parameters, it costs $191 million just to pre-train, just the pre-training costs. Not including labor, not including chips. The chips alone on the order of $1 billion, right? No one in this room can claim to be able to even ask for that much resources. When I was at DARPA, I couldn't ask the director for $200 million just to train an AI model. And so this is one of the more pervasive gaps, I think. It's the fact that we're seeing a kind of gatekeeping of AI. If you want to develop the best models, there's a handful of companies that are willing to throw this many resources at the problem. And so that's the first gap, and it imposes this kind of funny paradox where there are problems we can't afford to look at and also can't afford not to look at, right? We can't afford because we don't have the money. If you want to, explore, let's say, novel cancer treatments, et cetera, do you have the internet scale data and all of this money and all of these chips to explore the problem? Typically not. And this is in part because we abide by this kind of what I call implicit hypothesis. When we look at AI models, to the extent that there are underlying features that we care about, we assume that if we have enough data, if we have enough compute, implicitly those features will be learned by the AI model, right? This is conventional machine learning, conventional deep learning. But in neurosymbolic AI, what we're trying to do is look at the explicit hypothesis. Can we take explicit domain knowledge, knowledge graphs, SMT solvers, ontologies, can we take classical symbolic methods and integrate them explicitly as opposed to relying on this implicit brute force approach? That's sort of the basis, I would say, of neurosymbolic AI. Like I said, I'm going to mention what that looks like in the case of autonomy and biology. But first, it's worth looking into why do we scale up in the first place, right? We're not just scaling up for the sake of gatekeeping or because it's a profitable business model for Google and NVIDIA. We're scaling up because it is actually very useful. And so it's good to look at this from a nuanced perspective. Why do we scale up? There's the empirical argument, right? So the scaling laws were coined by DeepMind in a paper called Chinchilla, I think in 2022. And it basically looks at the fact that if you scale up compute, the size of your data set, and the number of parameters in your model, you get this nice extrapolation of performance. And by performance, we mean accuracy in out-of-distribution data sets. Now, this is not really a law. It's the same as Moore's law, right? It's an empirical extrapolation. It's not a fundamental law. But empirically, it seems to work out. And that's why you see models get bigger and bigger and bigger, right? We started with 1 billion parameter models. We're at 1 trillion now. But there's more than just the empirical argument. There's very good theory as to why we're making these models bigger and bigger. And so I want to give you the arguments. I want to steelman the argument for large models so that then I can present the counter argument for how we get to smaller, cheaper, democratized models. And theoretically, if you're training a neural network, what are you really doing? You're optimizing a loss function. The loss function is your proxy for whatever problem you're trying to solve, right? If you're training an object detector, maybe your loss function is mean square error. It's differentiable. You can compute how you have to change each parameter with regard to the loss function to optimize it. So let's assume this is a loss function. This is what is known as a manifold, high-dimensional nonlinear curvature. And we want to get to one of these nice peaks. Typically, you want to get to a nice flat peak. Now, it's very easy to get stuck in local optima. But the more parameters you have, the more directions along which your gradient can travel. So when you're training a neural network, the more parameters you have, the easier it is to get unstuck from local optima. So it makes perfect sense to make these models as big as possible. There's also been studies that show that a lot of these sharp manifolds sort of flatten out. You quite literally stretch out the optimization landscape when you make the models bigger and bigger, which means your basins of attraction become bigger and bigger, so they're easier to find. Lots of good theoretical reasons why these models are as large as they are and why they just keep getting large. But that raises a very critical question where I think neurosymbolic AI can play a prominent role. And the observation is the following. If you want a small model, something that is so cost effective that anybody in this room can build their own models from scratch, you're gonna have to deal with very sharp manifolds because you can't rely on scale to flatten your manifold. And so how can we do that? And we can begin by making a very sort of intuitive observation that whereas neural networks are very good at flat manifolds, symbolic systems are characterized by very sharp transitions. When we talk about SAT solving, you're switching from zeros to ones. When we talk about integer programs, you're switching from one extremal point on a polytope to another extremal point. They're very much characterized by sharp transitions in this manifold perspective. And so there's a high-level question, and this is based on a paper we published this year at PNS. There's this broad question of, can we train these small neural networks? And as soon as you're stuck in a sharp point, which we know how to measure, right? If your gradient becomes uninformative, you're kind of stuck. If your Hessian or the second order information of the neural network tells you you're in a sharp local region, you're probably stuck, right? We have very good ways to detect these things. When you're stuck, can you lift or convert that point on the manifold to an equivalent symbolic representation? A knowledge graph, an integer program, an SMT solving problem, whatever the case might be. And then we perform symbolic computations, not to solve the problem, because that would be too expensive, but only until we detect that if we were to project back to the manifold, again, we're in a smooth region, which is where neural networks excel, where gradient-based optimization of neural networks excels. So there's this feedback loop, switching between the smooth parts of the manifold using conventional training of neural networks, and then switching to symbolic computation when we encounter those sharp regions. And again, this is a fairly speculative idea, but if that were to work, it leads to at least two very substantial implications. The first one I already talked about. It's the fact that we could have cheap models that any of us could train without spending hundreds of millions of dollars. But the second one is probably just as important. It's the fact that we would be able to look at domains that have heretofore been very ill-suited for machine learning. What do I mean by that? When we think about machine learning, where has it truly been successful? It's truly been successful at conventional vision and language tasks. It has not been successful at combinatorial optimization. It has not been successful at logistics. There's some debate about how successful it is in robotics. I would argue it has not been successful in robotics. And I've seen in-person demos from NVIDIA and from a lot of these places of their robotic systems. They're nowhere close to what they make it out to be in the media. So really, it's conventional vision and language. Why is that? This goes back to a very fundamental assumption in machine learning. It's known as the manifold hypothesis. So the manifold hypothesis says that if you have a data set, even if it's very complex data, if the degrees of freedom is much smaller than the size of the data, and those degrees of freedom are shared across all of your data, then the manifold, the loss landscape will be favorable. It's going to be smooth, and machine learning will perform well. This is the case with vision and language. In vision, if you're detecting a face, faces are very complex, many pixels. All faces have eyes, a nose, a mouth. Manifold hypothesis is satisfied. If you look at language, a novel might be very different from an exam, but they abide by the same syntax, grammar, semantics. Manifold hypothesis is satisfied. But if you try a little thought experiment, let's say instead I'm looking at combinatorial optimization. I want to solve the traveling salesman problem. And I give you 1 million random traveling salesman instances. Is it the case that they all share some underlying simple features such that the manifold hypothesis is satisfied? I don't think so. I don't see how that could be the case unless they're all drawn from a very specific distribution, at which case generalization is a big problem. All of that is to say that there are all these other domains outside of vision and language where your manifolds are going to be sharp. And so dealing with sharp manifolds is a critical issue, not just for developing small models, but for achieving the same success that we have seen in vision and language, achieving it elsewhere. And so a lot of these arguments and all of the methods that I mentioned here is something we've been compiling into a book that was supposed to be published by now, but it's going to be published in February for anyone that's interested. And a lot of this came out of the work that I funded while I was at DARPA. And really this slide is to say that even though the idea I just presented is very speculative, neurosymbolic AI is already being used in so many different domains. And so I think there is a basis of confidence that neurosymbolic AI is mature enough that we can actually explore these kind of crazy ideas. And I can mention a few of these. Broadly speaking, you can characterize neurosymbolic AI in one of two bins, right? Going from the symbols to the neurons. So you give me your symbolic structure, LTL, knowledge graphs, whatever your symbolic structures are, how do I use that to guide the neural network, the training, the inference, etc. And then there's neurons to symbols. How do I use neural networks to extract the symbolic representation or to somehow guide the symbolic reasoning? And from symbols to neurons, we've seen symbolic structures being used in loss functions. I think the most famous use case and the biggest success story of neurosymbolic AI is PINS, physics-informed neural networks. A lot of people like to think that the symbolic and neurosymbolic AI has to be discrete for some reason. It doesn't have to be discrete, right? As long as something is governed by a semantically meaningful set of symbols, it's neurosymbolic. So physics counts. And people have looked at how do I integrate physics models as regularization terms in loss functions, leading to, in some cases, 10,000 times reduction in data. People have looked at how do you use knowledge graphs to modify the attention weights in a neural network. For those of you who don't know, attention is basically the most popular machine learning architecture right now. If you look at LLMs, transformers, diffusion, they all use attention as a backbone. So attention is a critical piece of architectures. People have looked at how do I integrate stochastic differential equations into diffusion models. Diffusion models themselves use a parameterized stochastic differential equation to denoise from one data distribution to another. So it provides a good avenue for you to bring in things like thermodynamics, which is governed by stochastic differential equations. Rewards in machine learning, that's sort of the obvious one. There's very easy ways to bring in symbolic structures into rewards. The whole reward machines literature is based on that. And I could go on and on. In the case of neurons to symbols, one that I think is interesting for this community is verification fine-tuning. This is starting to become popular, where you, instead of verifying the neural network, which is now intractable, right? There still is a community of neural network verification, but they scaled, to maybe 10,000 parameters. Neural networks nowadays are on the order of billions of parameters. It's very hard to verify a neural network in parameter space. But you can verify it in output space. If you make it output a structured representation and you verify it and you use the counterexample to modify your prompt, now you have Seeger. You have counterexample guided abstraction refinement during prompting. Now you have RLFMF, reinforcement learning from formal methods feedback, right? The verifier can rank order how many properties are satisfied. You train a predictive reward model based on that, and you now have a way to fine-tune your LLM to give you results that are more likely to satisfy your specifications. So this is a growing field of how we use verifiers. In fact, a lot of you are probably familiar with DeepSeek. You've heard of DeepSeek R1, the Chinese model that caused a stir earlier this year. They use verifiers in the loop. It's a very weak verifier. It's not a formal verifier, but they call them verifiers. And that's how they get their reward signal. So they're verifying the output and getting a reward signal based on that verification.
But you can also shield the learning with the formal.
Shielding you can also do, yeah.
So you don't need to do posterior verification. You are sort of
yes.
the learning.
Well, the advantage of the verification is you're using the verification to create a reward model that you can use to fine-tune the LLM to make it more likely to satisfy the specification. So these are complementary, the shielding and the verification fine-tuning. But yes, shielding, particularly in RL, is something we could easily add to this list as a neurosymbolic method. So all kinds of fun things going on in neurosymbolic AI. And with that context in mind, now I want to talk about the gaps. So the first gap is the gap from simulation to reality, right? We're not very good at modeling things in simulation, right? Despite what many people think, even our physics models that we have so much faith in, they're approximations. They don't actually capture the real world. The visual rendering, the sensor modalities, all of these things are approximations. And so there's a gap between what we model in simulation and the real world. And this is part of a broader field that goes by foundation models for autonomy, vision language action models, large action models. These are all synonymous. And this is the community that looks at developing LLM-like models that are trained on sequential decision-making problems. And the problem here is a lot harder than the LLM problem, because in the LLM problem, you have internet-scale data. In the autonomy problem, you don't have that. What you have are simulators, games, abstractions that act as data generators. So it's a very different kind of data modality. And all of these look different. The physics looks different, the visuals look different. So here I have one example. If you're training a foundation model for autonomous racing, here I have Deep Racer, Grand Theft Auto, and Carla. They all capture some aspect of racing, but they all look different. You can immediately tell that these all are different environments. And so there's a broader question of how do you reconcile these different interpretations? They all capture some truth, but none of them actually capture the real world. So this is still very much an open problem. But sometimes it works. So here I have one example. This is from another DARPA program called Machine Common Sense. And this is a fully autonomous Cassie bipedal robot that broke some kind of world record. And you can see it can kind of balance itself out. It's somewhat robust to the real world, to the idiosyncrasies of the track and so on. And so that garnered a lot of mainstream attention. It was featured on USA Today and so on and so on. But it paints a somewhat deceptive picture of where we are in robotics, because that problem is very easy to model in simulation almost perfectly. And so the same group, they did a follow-on experiment where they show just how problematic the sim-to-real gaps are. So here's a different problem. You have the same Cassie bipedal robot it has to learn to run while balancing two containers. And this is another problem we know how to model very well. So if you model very precisely the friction coefficients, the joint dynamics, the mathematical models for the containers, then 96% of the time that the robot runs in simulation, it will run in the target environment. And there's very cool YouTube videos of Cassie sprinting with the containers, and it's all very impressive. But if you increase that gap by a little bit, if you model everything very precisely except the mathematical models of the container, then the performance plummets to 0.1%, from 96% to 0.1%. And so this shows you just how brittle these systems are to symptorial gaps. And things become worse because this problem, in some sense, is a simple problem. It's sensory motor proprioception. All you have are the joint sensor readings. It's low dimensional. There's no vision stack. There's no adversary. There's none of this. So if you imagine what this kind of technology would look like in a military context, which we're already starting to see in Ukraine, for example, or in a safety critical context, or in any context where we don't really know how to model things that well, right? Underwater autonomy, space autonomy, anywhere where there's an adversary. These are huge symptorial gaps. And so the technology is nowhere near ready for the limelight. So what are companies doing about this? Because companies, obviously, they're very interested. There are a lot of autonomous companies looking at warehouse robotics. Meta is looking at robots that can clean your house. There's all kinds of autonomous operations. It's a huge market. They're scaling up, not surprisingly. I have more or less a direct quote from the last time I visited NVIDIA. We were talking about their Project Groot and Cosmos and their robotics projects. And I basically brought up these issues that I just mentioned. And I asked them, what is your strategy? Because clearly they're working in this space. And they said, and I quote, "We're going to throw as much data and compute at the problem until something cool happens." That's the strategy. And it makes sense for them. They have to sell chips, and they have enough chips that the strategy might actually work. Who knows? But surely there's a better way, right? I mean, I know there's a risk in anthropomorphizing AI, but clearly we can learn how to perform all these tasks using much less than $1 billion of worth of data and power and compute. And so that's something we started exploring under my TIAMAT program. TIAMAT stands for Transfer from Imprecise and Abstract Models to Autonomous Technology. It's a mouthful. It's also the Mesopotamian goddess of chaos, which is where I got my inspiration from. And for any of you that are interested, it was featured on the latest issue of the AAAI AI magazine. And the premise here is fairly straightforward. Instead of taking the conventional wisdom, which is have a very high fidelity simulator and generate an enormity of data, right? In the NVIDIA case, this would be their Cosmos model, which is a very new model. Can we instead take a diversity of low fidelity simulators, abstractions, games, things like Minigrid, Mujoko, Isaac Sim? Is there a way that we can leverage the noise in those low fidelity simulations and their diversity to generalize better? To some extent, you see this with LLMs, right? Part of the reason why LLMs generalize so well is they have very diverse text sources. They don't just take one text source. So in the robotics setting, to just take one high fidelity simulation is likely to cause you to overfit to that simulation. So in fact, there have been studies where robots overfit to the physics of one specific simulation. And when they encounter the physics of the real world, then they break down. So there is a power in having a diverse set of simulations. But then we run into some, again, fundamental issues. What does it mean for a simulator to be different than the real world? It's not clear. Mathematically, we don't have the vocabulary to say how these two things are different. If I show you the simulation here at the top, this is Deep Racer. At the bottom, you have a real race event. You can clearly tell how these are similar and how they're different. But no one really knows how to mathematically quantify that. What is the threat model? What is the robustness model, right? This is something that the adversarial AI community has been looking at for, I don't know, 15 years now. And even they have very trivial threat models, I would say. So for example, in the adversarial AI community, a very common threat model is the L-infinity norm. If you give me an image and I want to make sure that it's robust to imperceptible perturbations, you give me a budget, how much I can change each pixel, and then using adversarial training, et cetera, I can make the system robust to that threat model. Well, that threat model is useless, because if I were to simply change the clothes I'm wearing, the semantics of what's going on in this room would be the same, but it would incur an enormous L-infinity norm perturbation. And so there's a real need for more semantically meaningful threat models. And this is a very new field. It's known as, is it metric learning, norm learning? Basically, there are machine learning methods that are starting to look at how can we learn the right threat models that are semantically meaningful instead of these highly unrealistic ones. And we did a little bit of work in that space. Bernhard mentioned the Distinguished Paper Award from AAAI. That's what we received it for. It was looking at threat models over the dynamics, because one of the things that changes when you go from a simulation environment to the real world is the transition dynamics. If I'm in a specific state and I take an action, what's the probability space over my next state? That will look different in simulation than the real world. Because again, the physics are different, the dynamics are different. And so what we looked at is defining an uncertainty set over your transition dynamics. The real world exists within some KL divergence ball. Maybe it's a huge KL divergence ball, but it exists within some KL divergence ball of whatever transition probabilities you defined in simulation. So how can we turn reinforcement learning into a problem where you find the most robust policy to that uncertainty set? So instead of maximizing your expected reward, as you traditionally do in reinforcement learning, can you do a max-min problem? Can you maximize the minimum expected reward over the uncertainty set, over that KO divergence ball? And so we came up with a new Bellman equation. We call it a robust Bellman equation. And all of this work is in these, the whole screen doesn't show on here, that's weird. All of that work is in these three papers here. But it still doesn't really quite get at the semantics, right? Intuitively, yes, the real world exists within some ball of the transition dynamics, but how do you bring in actual formal semantics so that we can bring in symbolic representations? That's the key question, right? If we're looking at this from a neurosymbolic AI perspective, how do we leverage the symbolic to define these threat models and to define AI systems that are robust to large sim to real guys? And the intuition here is fairly straightforward. This is a very illustrative example. Let's say you have a robot, it's monitoring a building, and you want the robot to be able to detect doors. What is the traditional transfer learning wisdom? The transfer learning wisdom is collect a bunch of pictures of doors in your source environment, freeze all the weights, fine-tune the last layer on your target environment, and that's sort of a very conventional transfer pipeline. In this case, it would completely go out the window. If you're going from the environment on the right, which is mini-grid, to the environment on the left, which is the real world, these look nothing alike. Conventional transfer learning goes out the window, right? Doors in mini-grid are yellow squares. You interact with them, they turn into yellow lines. Looks nothing like a real door. So you could say that the sim to real gap between these two environments is enormous. They don't look alike. So then the question is there a level of semantic abstraction where these two start to look more and more similar? And can we define that symbolically? And can we use that symbolic structure to guide the learning and the inference process? So in this case, again, this is very illustrative. What is the semantic abstraction of doors? They're movable objects that are inside larger non-movable objects, which are your walls, such that when you interact with them, you're in a new area. That definition holds true across both of these environments. And it affords you new ways to ground your symbols, no longer just visually. You can learn what it means to be movable and non-movable through interactions with your simulation, like mini-grid. You can learn what it means to interact with a door and go into a new area by observing a large amount of entropy, right? When you go into a new location, you observe entropy. And so what that means is that when we try to transfer these more semantic representations, they will be more robust, because what will it take to fool a door in the target environment now? You would have to fool the visual detector, the functionally grounded detector that you learned in simulation, the information theoretic detector that you learned from observing large amounts of entropy, and so on. And so that's the broad question, is finding those shared semantic abstractions that hold true across all of these otherwise different looking domains. And so that's what we were looking at under that program. We're funding, I say we, I'm no longer there. Susmit Jha took over the program. I don't know if he's a part of this community. He's a big formal methods guy. And we're funding 14 universities and some small companies to look at both directions. How do we go from simulation to the real world? But also, how do you use the experience in the real world to refine your abstractions, to refine your simulations? Which I think is actually a place where this community could play a substantial role. It's the abstraction refinement piece of it. We have an autonomous Formula 1 competition. This is how we're testing our systems. This was my way to try to inspire students and postdocs and so on. So the kickoff meeting for the program last year, we held it at the Indianapolis Motor Speedway. And so during the breaks, the students could see the cars and so on. And whoever gets the best method is awarded $1.5 million. Spend it however they want. They can buy a house, watches, cars. So I think we have a good incentive structure to try to get some good methods. It's too late to participate, but yeah, it is what it is. But even if we solve that problem, on the horizon, there's always harder problems. So really what I would like to get to, or what I would like to convince my colleagues at DARPA to get to, is what does neurosymbolic AI look like on the edge? Because on the edge, you have very stringent power constraints. And on the edge, neurosymbolic AI takes a very different form. The neural tends to become the analog, right? When we think about a lot of spike timing dependent neural networks, a lot of neuromorphic computing architectures, they tend to be analog. Not always, but they tend to be analog. So the neural becomes the analog. The symbolic becomes the digital, right? Your application-specific integrated circuits, your FPGAs. And so neurosymbolic AI becomes an analog-digital kind of architecture on the edge. And I don't know what that looks like exactly, but I find it very interesting. But the motivation is that when we look at edge autonomy, industry can make two very strong assumptions that typically in the military and in some health sectors we can't make. The first assumption is that they're always connected to the cloud, right? So if you have your Amazon or Meta robot that cleans your house, it's technically an edge device, but it's always connected to the cloud. So the expensive procedure of training is deferred to the cloud. The robot just has to inference, which is very cheap. The second assumption is, yes, it's power constrained, but there's a power outlet that you can plug it into at the end of the night. It's not that power constrained. But when you look at things like underwater autonomy, space autonomy, intelligent medical implants, both of these assumptions are violated completely. They're not going to be connected to the internet, and they're not going to have a power source nearby. So I don't think that industry is well positioned to solve these problems. In the case of health, it gets even worse, because in the case of health, the power regimes, and here I've listed a few, they're on the milliwatt order of power. If you look at NVIDIA's edge GPUs, right, their power efficient GPUs, it's 10 watts, right? You look at Jetson, you look at Thor, you look at Orin, it's 10 watts. How do we get to milliwatts? There's a fundamental shift in the computer architecture itself that would have to take place. And I don't know what that looks like, but fun to think about. So that's broadly the gap in autonomy. That's broadly the TMAT program. So how am I on time, Bernhard? 20 minutes?
Yeah.
Okay. I think that's fine. So now there's this other gap. This is a brand new program, actually. The proposal deadline just passed. It's a program called NODES. And it looks at the gap between natural and synthetic biology. And a lot of this was motivated by a problem that should concern all of you, that is outlined in the White House framework for nucleic acid synthesis screening. Everything I'm going to talk about is public knowledge, nothing sensitive here. And basically, this framework looks at the problem where the US government is going to impose restrictions on manufacturers and providers of synthetic sequences. So if you order a synthetic protein or a synthetic DNA, starting October of 2026, it's going to be run through screening algorithms developed by NIST. And that's very important because there is an increasingly feasible threat of synthetic biological attacks, especially with how far bio-AI has come. So historically, what various security agencies have done is if you encounter an unknown substance, first you sequence it, you get a flat sequence, a string. It could be a protein, it could be DNA. And you want to determine, is this harmful or is it not harmful? We have two methods to determine this. The first one is very accurate. It's wet lab experimentation, actually physically run the experiments. But that takes weeks to months, which can be very problematic if there's an actual attack. The second one is very fast, but shockingly inaccurate, and that's database matching. So basically, there's a database of known regulated agents. If you encounter this unknown substance, you do a string similarity match to the agents in that database. And similarity here it's called BLAST in the case of proteins and DNA. And if there's a match, then you say this might be harmful. Now, historically, maybe that's been okay, but now that we can generate synthetic sequences, they might look very different from whatever is in those databases. So now there's a big push to develop AI that can predict whether something is harmful or not. This is particularly concerning if things weren't bad enough, because Microsoft, this is a paper, it was uploaded on bioRxiv last year, but it has since been published, I think, in Science or Nature, one of the big venues, where they did some basic adversarial attacks to bypass the screening algorithms of the big 4 companies that currently screen unknown substances, which is very concerning. Unlike in autonomy, where we don't know what our threat models are, in biology, we do know what our threat models are. If you want to perform an adversarial attack over sequences, your threat model is a radius of BLAST similarity. Basic local alignment search tool. It's a string similarity metric. If you want to perform adversarial attacks over 3D structures, we have PLDDT, the predicted local distance difference test. We have template matching scores. They basically look at how different things are in 3D space. And Microsoft, they did a very basic adversarial attack over these 2 threat models and bypassed the screening tools. So again, very concerning. But unfortunately, AI is not quite at a place where we can really predict the function of these highly synthetic substances. And there are a couple of good reasons why. First of all, the whole bio-AI community is very fixated on 3D structure. It's fixated on learning 3D structure from large static data. And that large static data has the bias of nature, right? Historically, all of the experiments we've done on biology are on natural data. So you have this problem of how do you generalize to synthetic data when all you have is natural data? And the synthetic data might look very different in terms of sequences and structures. And so here's a very good use case. This is, I think it might be the most popular model, I'm not sure, in bio-AI. It's called ESM3, Evolutionary Scale Model 3. It was developed by Meta, NVIDIA, Amazon, and eventually branched off into its own company called Evolutionary Scale. And they make this very nice lofty claim. The title of the paper is Simulating 500 Million Years of Evolution with a Language Model. Because what they do is they discover a new green fluorescent protein that is 500 million years away from any of the green fluorescent proteins we know today, which sounds very impressive. But when you look at the similarity to the training set, the sequence similarity, it's 58% similar to the training set. Why is that a problem? It's a problem because the rule of thumb is that 2 sequences are dissimilar if they bear at most 20% similarity. So this doesn't even meet the threshold for predicting something that is dissimilar from what we know, much less something that is highly synthetic, highly novel. I mean, something that's highly synthetic, maybe it's 10% similarity, maybe it's 5% similarity. So we're nowhere close. And this was trained on trillions. I didn't even know we had trillions of sequences. This is trained on trillions of sequences. So it's, again, these are some of the pernicious effects of simply trying to scale up. But the insight here, going back to the neurosymbolics of it all, is that similar to what we saw in autonomy, if we look at the raw data space, yes, the natural and the synthetic can look very different in terms of their sequence similarity and 3D structure. But at some level of semantic abstraction, they begin to look more and more alike. They abide by the same biophysics, right? The same thermodynamics, the same statistical mechanics, all of these things. And perhaps more interestingly, they abide by the same logic. So there's this very interesting phenomenon where a lot of biology is sandwiched between context-free and context-sensitive languages. So for example, RNA secondary structure prediction can be modeled as a context-sensitive language, which means you have a context-sensitive grammar that can generate valid RNA secondary structures, and a linear bounded automaton that can accept valid RNA secondary structures. Carbohydrate branching dynamics, context-free language. The graph structure of molecules, context-free language. So we have all kinds of very interesting symbolic representations that we can bring to bear that are really not being looked at as much as I would hope. And so this is the paper that shows how molecules are context-free languages. It's known as the selfies representation, or self-referencing embedded strings. And the intuition is fairly straightforward. If you think of a molecule, molecules have branches and rings. If you have a ring, as soon as the ring starts, you might imagine that you want to push onto your stack until you encounter where the ring originated, at which point in your push-down automaton, you want to pop from your stack and then go in whatever other branch you have. So the intuition behind why these things are context-free, once you work through an example, is actually fairly intuitive. But then that does bring about the big question, right? Going back to the implicit hypothesis versus the explicit hypothesis, whereas the bio-AI community has been so fixated on implicitly learning all patterns by optimizing sequence and structure similarity, we know that synthetic biology is going to be very different in terms of sequences and structures. But we can explicitly bring in biophysics and formal languages. That is the big question. How do we actually do that? And again, the vision that we want to enable here is twofold. We want to predict the function of novel molecules, and that will have to bring in a lot of biophysics. So I have one example here to really illustrate how complex this is, because it's not just predicting 3D structure, it's much more complex. Here we have an example of a viral nucleocapsid. And we want to predict whether this viral nucleocapsid kills the cell or not. What is the pipeline? You have to predict the 3D structure of the viral nucleocapsid. You have to predict how it interacts with the surface cell receptor proteins. Does it interact in such a way that it gets endosized, which means it enters the cell? If so, are the electrostatics within the cell such that the pH level changes to a point where the DNA inside the viral nucleocapsid swells and bursts out of its lipid membrane? If so, does it make it to the nucleus? If so, does it interact with chromosomes in such a way that it causes a gene translocation? If so, then either the cell dies or there's various cancers that are caused from these gene translocations, something that happens. But that whole pipeline involves thermodynamics, statistical mechanics, electrostatics. There's a lot of explicit biophysics that is not just 3D structure. So we're still missing that piece, and that's what that NOTES program looks at. So hopefully in the next few years we'll have an answer. But then there's a second application domain, and actually this is something, Bernhard, I really want to talk to you about, because I think this is a place where grammatical inference can play a very interesting role. And it's the discovery of new molecules. When I was trying to sell this as a program at DARPA, you have to make it very sexy, very ambitious. So I said, the discovery of a new basis of life. Can we discover a new DNA that sets a new foundation for life? Very lofty goal, probably won't happen. But we can discover new molecules, right? That's reasonable. For example, if you prompt an LLM and you say, I want to discover new DNA for fungi that can break down hard plastics, right? We currently don't have a way to break down polyethylene, which is sort of the industrial grade plastic. We know how to break weak plastics, but weak plastics are not as important. Or can you discover DNA for new bacteria that can heal space materials? Because once you're out in space, any kind of maintenance is almost impossible. So there's all kinds of cool questions you can ask. And the broader question is, given that these molecules are formal languages, specifically context-free languages. Is there a way to bring in grammatical inference to learn what those languages are? And so here I have a very illustrative example. If the prompt is that you want to develop a drug to treat lung cancer, these are two real molecules that have been used to treat lung cancer. The first one worked on many people, but apparently, so there's this protein called an EGFR receptor protein. When it's overactive, it leads to the lung cancer. So what you want to find is a molecule that binds to it in such a way that it inhibits the overactivity. The first molecule did that effectively for many people, but a lot of people have a mutation on their EGFR receptor, and it didn't work on those people. So it eventually had to be refined to the molecule on the right, and those are the molecules, the citations you see here are for those molecules. So the one on the right is an FDA-approved molecule, and the change is that red substructure in the molecule, okay? And so the broad question here is, can we ask membership queries in the active grammatical inference style? You know, we have very good conversational bio-AI models that can act as probabilistic oracles, right? Sometimes they hallucinate, sometimes they don't know. So they're a sort of probabilistic hallucinatory oracle. Can we ask membership queries from them such that we can build out a candidate automaton, which would be the first molecule here? Then we run an equivalence query. And again, with equivalence queries, I think the bio-AI community is at a point where we can use AI-accelerated simulation as an equivalence query. Back in the day, by which I mean 2 years ago, it used to be the case that if you wanted to run a high-fidelity molecular dynamics simulation, it could take weeks, even on a supercomputer. Now, people have used AI to predict what the simulation will be 100,000 times faster, so they claim. So finally, I think we're at a place where we can use those probabilistic predictive simulations as the equivalence oracle. That's what would tell us, no, for these humans, this molecule didn't work because they have a mutation on their EGFR receptor. How do we get a counterexample from that to ask more membership queries and do this loop until maybe we can rediscover these FDA-approved drugs and discover entirely new ones? That's sort of the big question. Now, this is simplified because, again, molecules are context-free. This works for regular languages, not context-free, but you get the point. The point is, I think there's a place for both active and passive grammatical inference to play a role in the discovery of molecules. I think the bio-AI models are finally there. 9:52. Okay, I'll be very, very fast. This is just one slide. Another thing we looked at was, this is through the FoundSci program, Foundation Models for Scientific Discovery. There's a very interesting gap in AI for science because the problem of transformational creativity, if you want an AI that comes up with a truly transformative idea, oftentimes that idea is going to invalidate previous theories, right? Switching from an Earth-centric model, switching from the miasma theory of disease to the bacteria theory of disease. And I'm not an expert in any of those areas. Those are just some of the famous ones. I know something about quantum mechanics, challenged relativity. I'm not an expert, but the point is when you have these transformative ideas, they challenge previously held assumptions. This is a very interesting problem for machine learning because what you're essentially asking is for the machine learning model to generalize so well that it invalidates its own training data. It's kind of a paradox in terms. So this is something that you could call it a defeasible or non-monotonic out of distribution problem. And thankfully, we do have some logics that look at defeasible reasoning, non-monotonic reasoning, right? This is the kind of reasoning where as you add more knowledge, more axioms, it can invalidate previous axioms, right? From a logical perspective, the logical entailment operation is not monotonic, right? For those of you logicians out there. And so there is some recent work on trying to treat this using a graph theoretic logic. No great results yet. This is sort of an open question. But I think this is one of the fun gaps where your training data has to be invalidated for you to succeed. So not sure what to do with that. So to conclude, a lot of these gaps, they're really an out-of-distribution generalization problem. But the particular form that it takes and the methods that we'll need differ across all of these. And it's very different from just conventional vision and language. In the case of autonomy, it's the gap from simulation to reality. In the case of biology, it's the gap from natural biology to synthetic biology. In the case of AI for science, it's the gap from exploratory or combinational ideas and creativity to truly transformative creativity. But across all of these, the intuition is the same, that even though these gaps in their raw representation are substantial, at some level of semantic abstraction, we have symbolic structures that we can bring to bear, right? In autonomy, we had dynamic scene graphs, knowledge graphs, etc. In biology, we have context-free languages, we have biophysics. And in AI for science, we have various kinds of non-monotonic and defeasible logics. So how can we bring those symbolic structures to bear to close these gaps? These are all open problems. And I'm happy to chat more, happy to collaborate. And with that, please feel free to shoot me an email, and I thank you for your time.
Thank you very much. Is it on? Yeah, so I just have to eat it and it works. So thank you very much for the inspiring talk. We see the good thing is good news. It seems to be there's still something left for us to do. Wonderful.
Yeah, there's always. Yeah.
And let me just do it. Of course, Kim. Yeah, okay.
Thank you very much. I was curious about this learning semantic abstractions. Maybe one should not learn everything. I mean, in formal methods, you start by a human writing high-level specification and then refine them. So I was thinking about your doors. I mean, I would not aim at learning semantic abstractions. I would actually have, a developer actually start by writing specifications.
Yeah.
And then this would be an enormous assistance in the learning. So how could you say something
I agree.
about?
Yeah. And that's where we should start, is leverage the domain knowledge. Don't make things more complicated than they need to be.
So this, yeah.
Yeah, the learning the semantic abstractions becomes much more relevant in the bio-AI setting, because we don't know in advance what the molecules are, so we have to, yeah. But in autonomy, yeah, we have a lot of domain knowledge.
Thank you very much. Very interesting, especially to me. I work in implementing human-like inferences altogether, like deduction, but also abduction, which is non-monotonic, abstraction, argumentation, and induction in the logic part. So you just quickly touched upon this, but I would like to know how much perspective is there for applying these technologies together with the neural part, and especially induction. So machine learning also on the logic part. Thank you very much.
Yeah. When you said these technologies, I kind of missed which technologies? Like just symbolic methods in general, or?
Yes. Automated reasoning through
deduction,
induction, abstraction.
Yeah. We're starting to see a lot of that, mostly in the AI for math community. So the AI for math community has come a long way, and if you read, for example, Alpha Proof, Alpha Geometry from DeepMind, they claim it's a neurosymbolic method. It kind of is. It's a Monte Carlo tree search, and then each leaf node is expanded using a neural network. And then you have the basic rules of theorem proving. So it's easy to, in those contexts, it's easy to generate data, because as long as you're following the axiomatic rules, then you have a valid proof. So that's where a lot of the power comes from, is that when you look at data sets like ProofPow, for example, it's easy to take that data set and generate a lot more data that is technically valid. That's, I think, where the biggest success has been. Yeah.
Cool, yeah, thank you. Yeah, I'm a philosopher, so thanks for giving a talk that I found interesting and helpful, even though I lack all the technical knowledge.
Thank you.
So I was also interested in the doors. And so if I got your point correctly, the idea is, well, if you make these systems sensitive kind of to the content and not just to the vehicles, then it's much harder to fool them. Like, I hope that's the core idea.
Yeah.
And then I was wondering if, like, to stick with the doors, like, what do you really need to give them sensitivity to? Do they have to have, like, really a definition of what a door is? And then I guess there is like, oh, maybe there are some interesting philosophical questions that are adjacent. Like, do you need like necessary sufficient conditions? Could you do like Wittgenstein family resemblance stuff? Like, what kind of things do these systems really need to make them more robust?
Right.
That made sense.
Right. Yeah, your intuition is correct on the door example. And it is, in some sense, a philosophical question of what is a door. So this is, I've gone down this rabbit hole before, but there's a very interesting lecture from Noam Chomsky talking about the meaninglessness of words. So he talks about what is a river. And a lot of us would say, well, for one thing, a river has water, which is not true. If you say there's a river of sludge or a river of whatever, it doesn't necessarily have to have water. There's all these weird idiosyncrasies. So yeah, it depends on how you define a door. I think that the point there was that we can train models to be robust across multiple different modalities, not just the vision modality, but the functional modality of how you interact with objects and the information theoretic modality. And there's a deeper question there, because what an object is, as a community in machine learning, I think we have things very much backwards. So for example, if I train a machine learning model to tell me what a chair is, we typically take pictures of chairs, and it detects the object, chair, and then it infers that it's a place where you sit. But humans, that's not how we operate. We actually detect the function and infer the object, right? If I'm tired, I can sit on that table. For all intents and purposes, that table is a chair. And so there's a much broader question of how do you detect the function of an object as opposed to the object itself.
Thanks. Very fascinating talk. Another philosopher here with a profound philosophical question. So you mentioned these neuron to symbol approaches, and you also mentioned all these transitions in science between, say, classical mechanics and quantum mechanics. And we all know that quantum mechanics and gravity don't really work well together. So I mean, the transition from classical to quantum mechanics took the step of using very different mathematics, or using the mathematics in very different ways, like replacing functions with operators. And so if you want to approach, like if you want to use neural networks to discover new symbolic expressions, like how do you deal with the problem of finding the right symbol inventory, as it were, right? Finding the right language, basically, new mathematical language in which to talk about potential discoveries that you have not made as a human. What do you think about that?
Yeah, I mean, well, the answer is I don't know, but I mean, that's one of the deep problems. If you want to discover novel mathematics, that's an out-of-distribution generalization problem. What the community is trying to do is collecting enough data that the distance between the training distribution and the test distribution becomes smaller and smaller, right? At the limit of data, everything is in distribution and you're fine. I'm not a big fan of that. Again, this goes back to the scaling hypothesis. This is part of the reason why you want to scale up to internet scale data. There must be a more principled approach, and I don't know what it is. Yeah.
Okay, hi. So I'm also very much on the neurosymbolic side, in particular because I think that we should use the knowledge that we have when it is part of defining the solution that we are looking for, not as a constraint that basically cuts exploration where you are trying to explore, but when you are trying to converge, okay? Experience of over 10 years ago working with various groups in the AI community, being a formal methodist, where we basically were able to create, to solve synthesis problems, so to say, extremely efficiently, using a couple of logical constraints, and there were the other colleagues, number crunching from data and first principles, so to say, in a blind search for hours and days, okay? We were called the cheaters. So in a volume, okay, we were risking to be excluded from the solutions that would be presented because we cheated, okay? That's one aspect where I see that the human nature, in a certain sense, is a little bit, how could I say, playing against acceptance of other approaches, even if they are clearly more efficient and solve the problem. One observation. The second observation is working with non-computer scientists. They've understood that data is important, and data is like, the many pictures of the doors, etc. We are again behaviorists. I mean, that's the clear. I mean, functions, affordances. That's what actually moves the world. What can you do with things, to a certain extent, independently of the aspect and the phenotype, genotype, these kind of things, right? That's another problem. People don't get it. So have you encountered this before? Do you have a way of talking to people in a different way maybe or whatever, just to make them switch the mentality, the point of view?
Yes, I encountered, specifically when I branched out into bio-AI, I encountered a lot of that. And there are a lot of communities that don't understand the value, or even if they understand the value of data, they don't know what data should look like for it to be useful. And you see this a lot in biology, where they'll collect data that is extremely noisy. They'll throw away a lot of data that could be potentially useful to mitigate that noise. And that's been one of the big problems, is as soon as I went into biology, it's very hard to get the right kinds of data. I also faced a lot of resistance for some reason in biology, which was surprising to me. Resistance from not isolated incidents, many different groups, very resistant to my ideas. Even though my intent was, I didn't want anything from them, my intent was to fund them potentially and to come up with cool programs. And you would think with the successes of AlphaFold and all of these things that they would be more open, but in some ways I think it's made them more resistant. It's almost like they're trying to gatekeep something, I don't know. But yes, I faced a lot of issues trying to branch out into biology. I'm also not a biologist, so maybe that's part of the problem. They didn't take me as seriously.
Okay.
This actually goes back to the conversation Bernhard and I were having in the AI people not being so open to formal methods people that don't have an AI background. Yeah, you see it across disciplines.
Hi, thank you for that talk. Another philosophy question. So you described that program where you're trying to find a way to detect biosubstances that are dangerous. Aren't you, by that, building a system that could actually create those systems? And so why would they happen without the system that you yourself are creating?
Correct. That's the big problem, is that it's what we call a dual-use concern. And so the way the program was structured is that we decompose the problem of function prediction into its atomic components. And then we would fund separate groups for each. And we had a government transition partner that would integrate all of them into a access-controlled model, not an open source model. There's no good answer to the dual-use problem, unfortunately. But that's the best we could do. We already know of many groups that are trying to figure this problem out. So it's only a matter of time before somebody cracks it. And we need to get to it as early as possible with a secure access-controlled model. We're also implementing biosafety guardrails, so things like watermarking, things that are similar to shielding. It's not exactly shielding, but it works similar at inference time, so that if you ask what is the function of this molecule, and we detect that it might have some toxic functionality, you can steer the model in a different output. So there are some things that can be done, but there's no good answer. Yeah.
Okay, I think I have also a brief question which actually relates to the second invited talk. Do you hear me now? What?
Yeah, if you
okay.
speak in the microphone.
Yeah, okay. So one thing was, could you imagine, it's just because there was a talk on the power of embodiment, and if there it was about how you can get sentience. The question is, could you imagine in your cases that embodiment could play a major role, that you can, because you can interact?
Yeah, embodiment plays a huge role. In fact, there are various theories of mind around embodiment, right? The embodiment hypothesis that intelligence requires an embodiment of some sort. These AI models combine a few different theories of mind. The embodiment hypothesis, but also the compression theory of mind. They have to compress information in such a way that it is usable by the embodiment. So there's a few different, well, and an active inference theory of mind as well, because you're also minimizing entropy. So a lot of different theories of mind have to come together, I think, for autonomy to work. Yeah.
So I think, I think, thanks again very much. There's